Greetings, folks. Welcome. The practice of statistical inference involves using information from a sample of data to say something about a larger population. A common application of statistical inference is testing a claim you might have about a population mean or proportion. In this video, I'm going to test what's called a not equal claim about a mean value. And my specific claim is, I don't think that bottles of hair conditioner have an average of 17 fluid ounces. People that know me know that I am huge into hair products, so the first thing I do when I get a bottle of hair conditioner is I look at how much product I'm supposed to have in that bottle. And again, I have just the suspicion that I don't think that bottles of hair conditioner have an average of 17 fluid ounces. I'm not making a statement that I think it's more than 17 or less than 17. I'm simply saying I don't think it has an average of 17 fluid ounces. So, as always, you take your claim, and that's your alternative hypothesis. So, H subscript A is mu is not equal to 17. Again, this is a not equal claim about a population mean value. And I'm testing that claim against a null hypothesis that the average is 17 ounces. So that's written as H subscript naught is mu equals 17. The second step of our hypothesis test is saying the significance level. In this case, I've made a decision to test this at a 5% significance level. In other words, there's a 5% chance that I would make a type 1 error of rejecting the null in favor of my claim or in favor of the alternative hypothesis. So of course, the fun part, again, since I really love hair product, is to do the research. So I got 50 bottles of hair conditioner with all the hair that I have. I go through a lot of conditioner. And I found an average of, from that sample, of 16.8 fluid ounces with a standard deviation of 0.6 fluid ounces. So we use that information to calculate a test statistic. Here I'm just going to cut to the chase and show you those calculations. It's a t-statistic because it's a hypothesis test about a mean value. And it's 16.8, that's the value from my research, minus 17, which is the value from the null hypothesis. I'm dividing that by the standard error of the sampling distribution, which is 0.6, that's the sample standard deviation. Divide that by the square root of the sample size, which is 50. So here I'm getting a t-statistic of minus 2.36. Again, since this is a two-sided test or a not equal claim, you might get a t that's negative, you might get a t that's positive. Again, really the issue is, are you equal to 17 fluid ounces or are you something below? In that case, you get a negative t value, or you get more than that amount of conditioner, and then you'd have a positive t value. So to take that t-statistic and find the corresponding p-value, of course you have to go to the t-distribution table. You might remember that your standard t-distribution table shows an upper tail for given degrees of freedom. Since we had a sample size of 50 bottles of conditioner, we have 49 degrees of freedom. Of course, you look at this t-distribution table, you only see positive values, but bear in mind that the t-distribution is symmetric, so just like magic, you can turn all those positive values into negative. And now we're just at the bottom tail of this distribution, which is where you want to be because you have a negative t value. So we're going to look for a t of minus 2.36 and find the proportion or percentage of the distribution that corresponds with that. Of course, we can't find a value of minus 2.36, but with 49 degrees of freedom, we find a t-value of minus 2.010, and then right next to it we see a t-value of minus 2.405, so we know that that value of minus 2.36 is somewhere in between 1% and 2.5% in the bottom tail of the distribution. So that's really the first part of finding the p-value. Our t-statistic of minus 2.36 corresponds with between 1 and 2.5% of the bottom tail of the distribution. But since this is a two-sided test, you have to multiply that range by 2, and then you get a p-value of 0.02. That's 0.01 multiplied by 2. And then the other end of the range is 0.05. That's taking 2.5% and multiplying it by 2. And again, because this is a two-sided test, you multiply that area under the distribution by 2, so we have a p-value of between 2% and 5%. This is relatively weak evidence in favor of the null hypothesis. You might recall that the p-value is the strength of the evidence in favor of the null. So if you get p-values of like 0.2 or 0.5, those are large values. That's pretty strong evidence in favor of the null. But in this case, you're getting values of 0.02 and 0.05, which gives us a good sense that we might have enough support for our claim. But of course, to be sure, you have to compare that p-value to the alpha that you set as a researcher. I happen to set an alpha of 0.05, which means I was willing to tolerate a 5% chance of rejecting the null hypothesis when it's true. Because we have a p-value of between 2% and 5%, or between 0.02 and 0.05, there's between a 2 and 5% chance that if the null was true, you would get a test statistic that's as or more extreme than that test statistic we got of minus 2.36. In other words, the strength of the evidence in favor of the null is between 2 and 5%. So since the p-value is less than the significance level, or alpha that we set, we can reject the null hypothesis in favor of our claim. So we can say that with a 5% significance, and based on a sample of 50 bottles, bottles of hair conditioner don't have an average of 17 fluid ounces of product.